This is actually the first of two talks I'm going to give in this session for a couple of P&L colleagues who couldn't be here with us today. This work from Chris Johnson and team has been focused on how do we select the right tracers for experiments that are used to validate our subsurface and atmospheric transport modeling in support of treaty outcomes. So I'm going to talk about a few things here. Let me see if this is going to work. Here we go. So first, let's talk about in general what makes a good noble gas tracer. We would think about things like half-life. If you're going into the field and you're doing an experiment, you need a tracer that's going to persist long enough for your operations and provide sufficient resilience in case of bad weather or other things that may delay you. And so that might drive you to a slightly longer half-life than you might otherwise consider, for example. Relevance is very important. Is it a treaty-relevant radionuclide, or does it act as a surrogate for one of those? How are you going to make the measurements? Is this a real-time in the field measurement? Can you make that with this tracer? Or must you collect samples and bring them back to the laboratory? And last, how challenging is it to produce? Or how costly to produce the tracer for that specific experiment. So these are the kinds of things that we at P&L and Chris especially has been considering as we build these experiments to help validate our models. You may have heard Michael Fox's poster this morning on a chemical explosive experiment that we did with tracers underground. On Monday, Akshay Gowardhan talked about atmospheric tracer experiments that we have also done. And so these are exactly the kinds of things that we're talking about. How do we pick what kind of tracers we should use? So let me start with argon-37. It is an isotope of interest for nuclear explosion monitoring, and there's ongoing work to develop and improve fieldable systems to actually go measure it. Primarily, though, we collect samples and bring them back to the lab. There are some potential challenges for using argon-37, in particular at legacy nuclear test sites, and that's the presence of argon-39. So argon-39 has a much longer half-life and has a much higher energy range, and so it can contaminate the spectrum in the part of the 37 part of the spectrum. So it can create some background challenges. The 35-day half-life for argon-37 actually makes it valuable for longer-term studies of looking how argon moves in the environment. And compared to the other noble gases that we're considering here, it is one of the least soluble tracers. So really important for underground transport effects that it has the lowest impact on the water saturation in your geology. In that way, it's also an end member for those test cases. So how do we produce it? We irradiate argon-36. That can be complex and high cost. And again, as I mentioned, the detection of this right now requires collection of discrete samples, which we take back to a laboratory, although there's work ongoing in laboratory field system, or in fieldable systems. Let's talk about xenon-133, obviously critical isotope of interest. We have existing methods for sampling and detection in the field, and a 5-day half-life is workable if it's a short transport study, but it does present some operational timing challenges. We looked at 133, for example, for atmospheric tracer experiments, and I think we may still implement one in this way, but we do have concerns about what happens if we get delayed. What happens if we end up in a couple of rainy days in a row? Our tracer is decaying as we wait, and so that's one where just the operational constraints may present a challenge. And then I'll make one of Chris's favorite subsurface points, which is that noble gases do interact in the subsurface, and they interact differently from each other. So the rate of movement of, let's say, xenon through the subsurface will be different than argon, will be different than the other noble gases. And so an important point here is that the xenon absorption on zeolites in the surface can be very impactful on their transport underground, and that needs to be taken into account. It could be a point of study, but it's also important to note. Xenon 133 is produced by irradiation of xenon 132. It's available from medical isotope suppliers in various quantities, and has pretty straightforward real-time detection. It could also be done, of course, in a laboratory, so it's fairly straightforward from that perspective. 127 xenon is a tracer that we have used actually pretty extensively in the last several years. It's not a current isotope of interest for nuclear explosion monitoring. It's not produced, it's not a fission product. But it can be used as a surrogate for other xenon isotopes. And what's really helpful about it is, again, it has more than 30-day half-life. It's right in this sort of sweet spot of radioactive enough you can detect it, but the half-life is long enough that you can sort of operationally manage it. The way that we make xenon 127 is we have a high purity sample of xenon 126 and you irradiate it. Xenon 126 is very hard to come by, so this process becomes challenging and very expensive. But it does have a pretty simple, straightforward detection. It's got high energy gamma rays, and that makes it easy to detect in real time in the field, as well as to collect samples and bring them back. Radon. There was a poster in the session this morning about modeling radon in the subsurface using COMSOL, which appreciated that one. I think there's been some work in the past on using radon potentially as its own signature of explosions underground. Here we're talking about radon as a tracer. It's not necessarily an isotope of monitoring interest, but it can be a significant background. It's the thing that we need to account for. It's produced, of course, naturally. It can be useful for understanding borehole quality. So in our underground experiments, we drill boreholes, we collect gas out of the rock, and if that borehole somehow has a direct connection to our tunnel, that implies that our borehole is not sufficiently sealed, and we can detect that through changes in the radon background that we're measuring in real time. Of all the things that we've considered here, radon is the most soluble, so has the highest impact of water in the test bed, and so it's something that needs to be considered. Again, a possible way to get at some physics in terms of the transport to support validation of models. It's pretty easy to make radon. Anybody can do it on a benchtop. And it's also just present everywhere, so it's easy to find. The detection is relatively simple, alpha detection, commercial radon detectors, etc. So the other thing we've thought about and considered in this process is stable gases, so not radioactive at all. And the idea would be that you would want to perturb the natural abundance that might be present, whether that's isotopic or elemental. SF6 is another example of this that we see often. And these things are easy to purchase. And from a detection perspective, potentially by in-field mass spec systems, but often the sensitivities that we need really require collection and then measurement back at a laboratory. One thing I'll point out about all of our tracers in which we generate them by neutron irradiation on a different isotope, we almost always get that stable isotope for free. And we saw that for ourselves in our subsurface experiments where we were able to measure both the xenon 126 and the xenon 127 in our various collection locations. So conclusion, again, as Chris says, there's no perfect tracer for noble gas studies, and really needs to be chosen based on the needs of the particular experiment, especially considering things like its relevance, the physics we're trying to go after, the detectability, and the operational logistics. Chris's favorite point about noble gases not being perfectly unreactive, I'll point that out again. And it's really important to keep in mind for subsurface transport experiments, the solubility and the sorption considerations of the tracers that you choose. I'll say that the radioactive tracers can provide significantly improved real-time detection and direct measurement of isotopes of interest. So there may be a place as well for our stable tracers, but again, it's important to pick the tracer based on your specific needs for your experiment. And with that, I'll say thank you.
Thank you. We have time for a couple of questions. Yes. Yes, speak loud.
My question is about sorption of xenon in solid zeolite.
Yes.
Is that something you already study or integrate in your model?
Yes. So there have been a number of benchtop studies of xenon sorption in various materials. We use that data, we put it in our models, and some of our colleagues at other US laboratories do the same. It's an important element, or you will not get the transport characteristics correct.
Okay, thank you.
Yeah.
Interesting.
Question back there.
Thank you. Vladimir Krychenkov, Russia. My question is about background of argon-37. Argon-37 is a good indicator of underground explosion or quick process when it created from activation of calcium and sequential decay. But what I know just that there are several publications about background of argon-37 produced from argon-36 by neutrons and decays, several including the space neutrons. I don't know, but now the equipment is so sensitive, sampling analysis, that's, can you say, and it would be somehow misleading because it's not released from the underground, and of course not from nuclear facilities, but likely natural background. Thank you.
Yeah, thank you for that question. I will say this, we know a lot less about argon backgrounds than we know about xenon backgrounds, right? And a lot of that has to do with the fact that we don't have fieldable systems for argon out there measuring every day in different locations across the world to kind of tell us what this looks like. But I've seen the same thing that you are talking about, that argon-37, that there is a natural background that is generated through these processes. And I don't think we have a good handle yet on the impact of that.
We have a question online.
I have a question online by Anonymous. What about xenon-129 as a tracer?
Oh, okay. So I know that we have considered xenon-129, but it fails me right now with my jet-lagged brain what the emissions and decay for that look like. But maybe if there's an audience member who knows this by heart, could potentially answer this one.
Thank you for the question online.
Anyone to the rescue? Xenon-129.
We have 1 minute.
Or we'd be ahead of schedule.
If not, maybe we'll move to the next
Thank you.
session. Thank you. That's fantastic.